Okay, wonderful people. Thank you all so much for waiting. I'm sorry for the late start here, but welcome back to Calc 2. Today is a big day for us. So this is our first fresh lecture following exam 1, which means we are about ready to dive into the big part of this class, which is the part of the class that has to do with something called convergence. So that's where we're going. I'm gonna go ahead and turn this on. Started. Now your exams, I haven't finished grading them. All of my classes had exams last week and I am moving through them one at a time. Yours is 2 ahead. So I've got some Calc 1 tests that I need to grade and then I'll be getting to your guys' tests. So my goal is to have your tests graded by start of class on Thursday. And that's the usual rule for me, is 1 week. So this is section 4 of MAC2312. It's a lecture. And the date today is the 16th of February. Today is an exciting day because we're going to begin our discussion on this fancy word, convergence. So I want you to pay extra careful attention to the language today. The class makes a huge shift. And somebody actually, I thought I got a really neat email before exam 1 that I want to share. I got an email saying, you know, the sample materials that I showed seemed very wordy compared to the WebAssign problems. And is it or is it not the case that, you know, my materials that I generate have a lot of words in them compared to the WebAssign stuff, which is more like, you know, just calculate this integral. The reason for that is because the sample materials I've shared with people have been from later parts of the class. And the language becomes much more important later in the class. So what you'll find is that in the WebAssign problems, as we go further and further down, there will be calculation involved. But the main thing is you're going to try to answer a question. Does this thing converge or does this thing diverge? And that really isn't a very satisfying thing, like you click one box or the other. Underlying all of that is the logical argument that gets you to the answer to that question, convergence or divergence. So I want you guys to please try to mimic my solutions as you do your own work. So pay attention, pay very careful attention to the notes I write, especially the words, right? Not just the symbols, but pay careful attention to the words. And as you write your own solutions, try to write in full sentences, right? Meaning, you know, reasonable grammatical sentences with subjects and verbs and periods at the end, all that good shit. And make sure that what you're writing down makes sense. When you read it out loud, listen for it, right? It's a good thing to do to read out loud your own solutions to these sort of problems. We're going to be talking about convergence for a long time. Basically, between now until like the last 2 or 3 weeks of the class, we're going to be talking about convergence, which is like from now up to exam 2, and then a few weeks after exam 2, we'll also be talking about convergence. So this is by far the largest part of the course and the most important part of this course. All right, that's enough rambling. What the fuck does converge mean? Loosely speaking, if an infinite process leads to a clear and finite result, we say that the process or objects involved is convergent. Or converges. So I'm going to show my age here. Converge is not just an old hardcore band. It's a word that has several different meanings and depends on the part of speech that you want it to be. Convergent is an adjective. It's a descriptive word for a noun. So I can say that, you know, an integral is convergent, or that a sequence is convergent, and it's a descriptive word for it. If I want to describe that interval converging, then the verb is just converge or converges. So I would say this integral converges and therefore is a convergent integral, or this sequence converges and therefore is a convergent sequence. Adjective, verb. We're going to have like 4 or 5 different notions of convergence corresponding to like integrals, sequences, series, and power series. So this is not a technical definition, but in the back of your mind, converging is the good thing, right? Converging is what we would like a series to do, or what we would like a sequence to do, or what we would like an improper integral to do. We would like them to converge. The converse, if that process or object fails to have a clear answer, or value, or yields an infinite value or answer, then we say that the process or object is divergent. Not like the horror movie, but just as a counter, an opposite to convergent, whose verb form or diverges. So again, verb, adjective. The first type of object to which we're going to assign these terms are integrals, but a special kind of integral. The regular integrals we've dealt with so far are all convergent. They're trivially convergent. It's not even a matter of like, there's no question. But for the types of integrals I'm going to introduce today, you'll see that there is a question, right? There's a kind of built-in question about whether or not there even is a reasonable answer. These will all be definite integrals. Indefinite integrals, these aren't things we can even ask about. And there will be special types of definite integrals called improper integrals. So the section we're beginning is section 7.8. And it's on improper integrals. And these will be the first objects to which we assign a notion of convergence. An integral is improper. So, if the area, or I should say, if the region whose area is measured by the integral is of infinite length, I'll say infinite width, or infinite height. And this is the mathematical or, meaning it's not exclusive, right? If both of these things are true, then certainly the integral is improper. So an integral is improper if the region is of infinite width or of infinite height. Infinite width, we'll call these type 1 improper integrals. Infinite height, we'll call these type 2 improper integrals. And this definition is kind of an intuitive one again in terms of sort of geometric concepts. I will give you a strict, in terms of algebra and calculus definitions, but this is what you should keep clear in your head. If the region whose area is being measured is infinitely long, like infinitely wide, then you're talking about a type 1 improper integral. And if the region being measured is infinitely tall, then you're talking about a type 2 improper integral. So how could this even be? How can I set up an integral that measures an infinite width area? And shouldn't that all just automatically have infinite area? And same thing for height? The answer to those questions are surprising. As is often the case when one starts fucking about with infinity, weird shit can happen. So let me show you what it is we're talking about. I'll hold here just for a second or two in case we need to get anything down. Okay. All right, turning the page in 5 seconds. Okay. So imagine I want to find all the area bounded by f of x equals 1 over x cubed from x equals 0 to x equals infinity. All of it, all the area under x cubed to the, oh, sorry, let me change this, x equals 1, sorry. From x equals 1 to x equals infinity. Normally writing something like x equals infinity, this is a bit of a faux pas. So if we wanted to say this more carefully, we would say all the area bounded by x cubed for x greater than or equal to 1. That would really be the right way to say this, but what does that look like? Well, let me draw the graph of 1 over x cubed. Here's the graph of 1 over x cubed. As we get close to 0, 1 over x cubed blows up. We've got a vertical asymptote here. I don't care about that because I'm paying attention to everything to the right of 1. So I'm talking about finding all the area to the right of 1 under this graph, right? Talking about trying to find all of this area. And it goes on and on and on forever. The way I would represent that as an integral is integral 1 to infinity 1 over x cubed dx. Now there's a clear issue here. The clear question is this area finite or infinite? It goes on forever and ever and ever out this way. So it could totally be infinite. That's a possibility, right? I mean, if the height always stayed 1, then this would clearly be infinite, right? Because you'd have a rectangle whose height is 1 and whose width is infinity. But we know that 1 over x cubed, it actually sits down on the x-axis. It sits down on the x-axis pretty hard. And the way you calculate an integral like this is by saying, okay, instead of finding all of that area at once, I'm going to stop at some capital R. And then I'm going to send R to infinity. But the order here matters. So we calculate this as the limit R to infinity integral 1 to R of 1 over x cubed dx. So the idea is that this integral tells you how much area there is under this function from 1 to R. And if I want to know how much area there is all the way out to infinity, I find a formula for the area from 1 to R, and then I send R to infinity in that formula. Now this integral we can crunch out. This is not terribly hard, right? This is lim R to infinity integral 1 to R x to the negative 3 dx. All right, 1 over x cubed is x to the negative 3. That's a straight up power rule integral. So this is lim R to infinity, and my antiderivative here, if you add 1 to this power, you get negative 2. So the power here, this is x to the negative 2. And then I have to divide by that new power. So there's a negative 1/2 here. I don't know if you can see the negative. Let me do it like this, negative 1/2, like that. And this apparatus has to be evaluated from 1 to R. Now I can clean that up algebraically a little bit. That's lim R to infinity, negative 1 over 2x squared, evaluated from 1 to R. And now I can go ahead and evaluate and then take the limit. So when you plug in R, you'll get negative 1 over 2R squared, minus when you plug in 1, you'll get negative 1 over 2 times 1 squared, which is lim R to infinity, negative 1 over 2R squared plus 1/2. So remember back in section 2.6 in the start of Calc 1, when you learned all those rules for limits at infinity? This is why, because that shit is going to be hugely important here. Not just here, but in every section of the textbook after this. As R goes to infinity, R squared goes to infinity. So this is like negative 1 over 2 times infinity squared plus 1/2. 1 over infinity squared is 0 for sure, right? If you take 1 and divide it by 2 times some enormous number squared, you're going to get something very close to 0. So this is 0 plus 1/2. So the area is finite. And we say that the integral from 1 to infinity of 1 over x cubed dx converges to the value 1/2. Oops, sorry, cut off on the side there. I didn't realize. Say that this integral converges to the value 1/2. That's how we use the language. So converge is a transitive verb, right? It has a direct object. It's the integral which did the converging, and it converged to the value of 1/2. You want to learn the language and use it correctly. I see a lot of people say things like converges at 1/2 or converges with 1/2, and that wouldn't be correct use of the language.
Wait, so isn't it still technically infinite? Like, even though you're getting closer and closer and closer and closer to the x-axis, as you still go on, it should be infinite, right?
Yeah, well, that's the fun question, right? That's the whole point. So this area, even though the region is infinitely wide, it gets short enough, fast enough, that if you were to roll it all up, it's a finite amount of area. Shocking
I
shit.
don't understand that, but for the purpose of this class, I will believe you.
I promise it's true, right? So the area, think of it this way. The area from x equals 1 to x equals r under 1 over x cubed is 1/2 minus 1 over 2r squared. That's what we just found. So if you want to know what's the area from 1 to 5, you'd plug in 5 for r. If you want to know what's the area from 1 to 10, you'd plug in 10 for r. If you want to know what's the area from 1 all the way out to infinity, you send r to infinity. And it turns out that just because of the way this antiderivative looks, because of the formula we're able to find for the area from 1 to r, happens to come to a finite value as you send r to infinity. It's kind of shocking. I agree that this is kind of shocking. The core idea here, that somehow you can have a region that's infinitely long, but still has finite area, should bother you. That's very counterintuitive. But it's true. And what we want to start asking ourselves is, what are the necessary conditions? Why? What the fuck allowed that to be a finite amount of area, even though it's infinitely long? Here's one way you can picture it. Zero less than y less than 1 over x cubed. And then less than x less than. All right, here's the area in question. Let me add in the graph here, 1 over x cubed. Let me fuck with my scales a little bit. Y, we're going to go from negative 0.1 up to like just 1. Okay. Here's this red area. Yeah? Maybe damn it. All right, here's the area we're interested in. And we want to let this go all the way out to infinity. The thing that's going on in the back of our mind, the reason it's possible for this to be finite is because the blue function goes to 0 so fast that out here, like the little bit of area from here on out is actually very small. Even though it's infinitely long, you can sort of roll it all up, and all of the area out here, even though it's infinitely wide, it does go on and on and on forever. It's actually such a small amount of area from over here that most of the area is right here. The height is so small that even though the width is infinite, the total area is finite. The only way this can work, and you should start asking yourself, the only way this can work is if this curve goes to 0. And it turns out going to 0 isn't enough. It needs to go to 0 really fucking fast. 1 over x cubed does go to 0 fast enough for this to work. But let me show you another example. Let's evaluate the integral from 1 to infinity of 1 over x dx. 1 over x also goes to 0. All right, here's the green function. 0 less than y less than 1 over x, and then x, let's do 1 less than x less than 20, similarly. All right, red area, purple area. The green function is 1 over x. And I think we would all agree that the green function, at least to the right of 1, is bigger than the blue function, right? The blue function is underneath there. So the red area is smaller than the purple area, yeah? How much smaller though? You see, the red area is so small that I can like roll all this infinite length up and get a finite length. But is the purple area small enough that I can roll it all up and get a finite amount? It's hard to say.
It doesn't seem like it's decreasing too much. So probably
Yeah,
not.
I mean, definitely both of these functions decrease and both of them decrease to 0. But does the green function decrease fast enough so that all that area is finite?
No.
Question. Yeah, and Cody's correct. The answer here is no. Let's see why.
Harmonic series, if you split it out into its parts, you can add it to 1, to 2, to 3, etc.
Well, so comparing this to a series is something that will come much later. We want to get comfy working with these directly because the duality between the integrals here and the series things that you're talking about later will usually go in the other direction. Usually we're going to say the series does something because the integral does something. So in a sense for us, this is the more foundational object, although it could be argued that the other direction is more important from some perspectives. Just like with the last guy, the trick here is to find a formula for the integral from 1 to r and then send r to infinity. So we rewrite this as limit r to infinity, integral 1 to r, 1 over x dx. And what that integral is doing is it's finding a formula for the area from 1 here out to some number r here. And once we have a formula for this area, I'm going to send r off to infinity. That's the idea. So the integral of 1 over x, that's the natural log of x. And notice that I'm rewriting my limit every time. I'm being very careful with my notation. You also need to be very careful with your notation. Do not get sloppy on this shit. Don't keep writing infinities up here. You need to replace them by some finite variable and then have your limit as that variable goes to infinity. Integral of 1 over x is the natural log of the absolute value of x. And this gets evaluated from 1 to r. So this is the limit as r goes to infinity of the natural log of the absolute value of r minus the natural log of the absolute value of 1. This guy is 0. So we have to ask ourselves, we can ditch the absolute values. R is going to positive infinity. So this is just natural log of r. R is definitely a positive number. What does the natural log function do as its inside gets bigger and bigger and bigger?
It decreases.
Increases to infinity.
Yeah, it does. It increases to infinity, and it does it slowly. So if we zoom, this is the graph of the natural log, right? This is a graph we certainly should know. And it might look like this guy has a horizontal asymptote, but if you go out far enough, you'll see that he just keeps getting bigger and bigger and bigger. He does it very, very slowly, but he will eventually go above any horizontal line you set. So remember, the range of the natural log function is actually all real numbers, right? It might not look like it, but this piece does grow up bigger and bigger and bigger and bigger and bigger. So the limit as r goes to infinity of the natural log of r, this is plus infinity. So here we would say the area under 1 over x from x equals 1 all the way to x equals infinity is infinite. Thus, the integral from 1 to infinity of 1 over x dx is what we call a divergent integral. All right. So just two quick examples to get us started. The 1 over x cubed integral from 1 to infinity, and the bounds matter. If you change the bounds, the result can change. The 1 over x cubed integral from 1 to infinity is convergent because there is a definite answer to how much area is there. 1/2. It's finite. The integral from 1 to infinity of 1 over x is divergent because the area underneath that curve, everywhere to the right of 1, turns out to be finite. This should fuck with your head a little bit. It shouldn't feel good. It should feel weird, but it's true. There are geometric arguments that you can make, but the simplest argument is the one right here. Here's the area from 1 to r. We get a formula for that in terms of the variable r. And then as we send r to infinity, we get infinity out. Okay, so that area's got to be infinite.
Just so I get this vocab right. So a divergent function cannot diverge.
Say that again?
Like, you know how you said the past function, it converges to 1/2?
The
This one's-
integral, yeah, the integral
Yeah.
from 1 to infinity of 1 over x cubed converges to 1/2. Yep.
So this one cannot diverge, like it's just divergent.
This integral is a divergent integral. Yeah. It's not the function that diverges. It's not 1 over x that diverges. It's the integral from 1 to infinity of 1 over x that diverges. So I'd say this integral, the integral from 1 to infinity of 1 over x dx is a divergent integral. If this answer had come out to some finite number, then I would say this integral is a convergent integral. But it's not 1 over x itself that diverges. 1 over x is just the function that we're using as the boundary. The thing that diverges is the integral, which measures the area under the function. Does that make sense?
Yep.
So every time we got infinity as an answer, that's divergent, right?
Yes, if the answer, the area you get out from your integral is infinite, then that is a divergent integral. So let me go ahead and formally define these. Oh, sorry, go ahead, Hans.
Can also happen if we get like negative infinity.
Yes. Yep.
Okay.
Let me go ahead and give the proper formal definition. These are type 1 improper integrals. We'll have a different rule and definition for type 2 improper integrals. So here's the formal definition. And convergence criterion. I'll just say convergence rules for type 1 improper integrals. So if you have an integral of the form a to infinity f of x dx, where f of x is continuous on the interval a to infinity, then we define this. Then we define integral a to infinity f of x dx to be the limit as r goes to infinity, integral a to r of f of x dx. And if this limit gives a finite value, then we say the integral, which I'll call up here 1, the integral 1 converges. And we would say converges to that value. If, so converges, that's what we're defining. If the limit is not finite or fails to exist, then we say, the integral one diverges. All right. Now it's important that this function is continuous. That's what guarantees that we're only talking about infinite width and not also talking about infinite height. They're absolutely, so Alejandro asked a cool question in the chat. Is there a relationship with Zeno's paradox? Yes, there totally is a relationship with Zeno's paradox here. I don't want to burn too much time on that, but Zeno said something like, well, you know, if I only ever take like if I want to close the gap between me and this wall, I have to first walk halfway to the wall. And then I will have to walk halfway from there to the wall, and then halfway from there to the wall. So I'll never get to the wall. I always have to take another half step. He was wrong. Zeno's paradox is not a true statement. But there is a connection here, yes. So this is our definition of a type 1 improper integral of the form a to infinity. There's another sort of type 1 improper integral. These are all type 1 integrals. You could also have something like integral negative infinity up to a of f of x dx, where f of x is continuous on the interval negative infinity up to a. This is an open parenthesis here. And the same rule applies here. In this case, we would define the integral from negative infinity to a of f of x dx to be the limit as r goes to negative infinity, integral r to a f of x dx. And the same rule here for convergence is true. If that limit has a finite value, then we say that the integral converges. If that fails to have a finite limit, then we say the integral, whatever, 1 or 2, diverges. It's important that the function is continuous. Again, that's what guarantees that we're only talking about infinite width and not also infinite height. And it's very important anytime you see anything like this, your very first step must be to rewrite it as a limit of a proper integral. I want to talk about some of the challenges behind computing these, some of the theoretical challenges, because those are meaningful and important. Why do we do it like this? Why isn't there some more direct attack? The answer is because you can't build a Riemann sum. Remember, the first step to defining any integral is to write down a Riemann sum for that integral. That's how our definite integrals are defined. The first step in writing down your Riemann sum is to calculate delta x. And delta x is always b minus a over n. You partition your interval, a to b, into some finite number of finite length pieces. Those are very important. You need both a finite number of pieces and they have to each be of finite length. The way you learn to do it in Calc 1 is by picking delta x to be b minus a over n, so they're equal length finite subintervals. There's no way to take an interval like 1 to infinity and chop it up into equal length finite subintervals. Either one of those intervals has to be infinite in length, or you need infinitely many of them. If they're all going to be finite in length, then you need infinitely many of them to cover an interval like 1 to infinity. So the reason we have to start by writing our improper integrals like this is because this motherfucker right here has no Riemann sum. Since he has no Riemann sum, he doesn't obey the fundamental theorem of calculus, and that's really important. Integrals like integral whatever, a to infinity f of x dx are called improper because we can't construct Riemann sums for them. This is because delta x for any such Riemann sum would be b minus a over n, which would be infinity minus a over n, which is infinity. So either our subintervals are infinitely long, and that's not helpful. That means each of my rectangles would have infinite width, so I'm fucked there. Those are all infinite. Or if we force delta x to be finite somehow, like say I'm just going to take delta x to be 1, you know, I'm going to throw out this formula from Calc 1 and say instead of that, I'll just have all my subintervals be length 1, even if you do that. Or if we assign delta x a finite value, there will be infinitely many subintervals. In other words, i.e., these are not Riemann integrals. And that means there's no fundamental theorem of calculus for these. And that's a problem because the fundamental theorem of calculus is the tool that we use to evaluate all of our definite integrals, right? We find an antiderivative, we plug in the endpoints. That is FTC2. The fact that you can evaluate a definite integral by finding an antiderivative and then plugging in a and b and subtracting them in the right order, that is FTC2. Well, if you don't have a Riemann integral, then you don't have a fundamental theorem of calculus. And since delta x has to either be infinite or we have infinitely many subintervals, we don't have a Riemann integral. So you cannot jump in and evaluate an integral like this directly using FTC2. In other words, you can't just take the antiderivative, plug in infinity and plug in a. That doesn't work. Not only is it improper notation, it will give you the wrong answer if you're not careful. So we always must begin by rewriting these as a limit of a definite proper integral. This thing, since we have the understanding that for this integral, we're not taking the limit yet, we're going to take the limit later, r here is understood to be a finite number, perhaps large, but finite, which means you can apply the fundamental theorem of calculus to this integral. You apply FTC2 to this, get your formula for the area from A to R, then send R to infinity. And that gets you around this real big problem down here of these things not being Riemann integrals. This might take a little bit of time to think about, depending on how much you remember from your Riemann sum stuff. But this is the big problem, right? You don't have a finite delta x. If you force a finite delta x, then you'll have infinitely many subintervals. So what you're talking about here isn't a Riemann integral, which means no FTC2, which means the shit that we've used in the past doesn't work, unless you begin by rewriting them as limits of finite length integrals. Then you've got an FTC2 here, then you can take your limit. So this is how we define type 1 improper integrals. If you've got an integral from like 1 to infinity or 2 to infinity or -3 to infinity, you write that as limit r to infinity, integral 1 to r or 2 to r or -3 to r. Then you solve that integral, then you take the limit. It's also possible to integrate from -infinity up to somewhere, and you do the analogous thing. You just have to remember you take the limit as r goes to -infinity, and then integrate from r to a, and then take the limit. So I'd like to show you guys a couple more examples.
Can you move down a little, please?
Move this like this.
Yeah.
Sure. So yeah, I'll hold here for a second. Basically, the tools that we developed in Calc 1 and so far in Calc 2, they're not enough on their own to handle these integrals. But once we rewrite them like this, we can apply those tools. We can apply those tools to this part and then take our limit. There's one case that's not covered here, and that's what about an integral from like -infinity to +infinity? And the answer there is you split them up. I'm gonna turn the page in about 5 seconds. Okay. So another note, and this is important, not just important concept-wise, but important for like calculations, the purpose of problem solving. Note. Integrals of the form integral -infinity to infinity of f of x dx. These we have to first split them up. This will be like integral from -infinity to some number of f of x dx plus the integral from that number to infinity of f of x dx. And you get to pick a. Then each one of these gets their own limit with their own variable. So this would be like limit r goes to -infinity, integral r to a of f of x dx, plus limit as s goes to +infinity, integral a to s of f of x dx. And it's important that you use different variables for these. There is another way of interpreting integrals like this. It's called a symmetric integral, where you do the limit as r goes to infinity of the integral from -r to +r. But that runs into some problems. So this is how we define integrals like this. I'll ask you to trust me and stick with it like this, because the other way, the symmetric definition can run into some really counterintuitive problems where the area is infinite, but happens to cancel in a beautiful symmetric way and give you something finite. We still want to call those divergent integrals because the area there is still infinite. And then one more little note. If any portion of an improper integral diverges, then we say the whole integral diverges. So like if you split an integral like this up, as you must, and this first guy is finite, but the second guy is infinite, so this piece converges, this piece diverges, then we would say the whole thing diverges. Doesn't matter that part of it is finite. If any part of it is infinite, the whole thing we say is divergent. All right, and with that, we're ready to do some more examples.
Can I ask a question before we go on?
Sure, please.
I wanted to go back to the example where we had 1 over x cubed. And if we had the bounds like we have now with the infinity to negative infinity, with that one, what do we do with 0?
Something else. That's a type 2 integral. So far we've only talked about how to define type 1 improper integrals. If you have an infinite discontinuity somewhere, if your function blows up to infinite height, then that is the other type of improper integral. Those are called type 2 integrals, and I will show you how to handle those. But first, we need to practice with type 1s.
Thank you.
Yeah, no, it's a good question. So let's look at the integral from -1 to infinity of x e to the negative x dx. How do I get started here?
Limit is r approaches infinity from -1 to r of the integral of x e to the negative x dx.
Very good. We have to begin by writing this as a limit of a proper integral, because only then, like not only do I not have FTC2, I don't have trig sub, I don't have U sub, I don't have IBP, I got nothing until I rewrite this as a limit of a proper integral, because all of those things are predicated on the theorems from Calc 1. So now that I've rewritten this as a regular proper Riemann integral, now I can apply all the tricks we know. FTC2, IBP, trig sub, U sub, whatever you want. You can only do that here. You cannot do it here. How do I evaluate an antiderivative for this sort of function?
IBP.
Good. So to begin the IBP, I have to pick U and dv. If I follow my Lipet rule, I don't see any logs, don't see any inverse functions. I do see a polynomial function. This x right here is a polynomial function. So u is x, and that means dv has to be everything else, e to the negative x dx. If u is x, then du is dx. If dv is e to the negative x, then v is e to the negative x divided by -1, which is just negative e to the negative x. So that's my IBP table. And now I rewrite this as, you got to be very careful here, limit r to infinity. And then everything that comes out of my IBP, I need to take the limit of. What comes out of the IBP? Well, this is also a definite integral. So I'll have u times v evaluated from a to b. That's bracket negative x e to the negative x evaluated from -1 to r minus the integral from -1 to r of v du, which is -e to the negative x dx. So there's really quite a lot going on here. When you do integration by parts with a definite integral, you must remember to evaluate this first piece. People forget that a lot. Got to evaluate this first piece. And then also the integral that pops out is a definite integral. And all of the bounds are the bounds from the previous line. I can do the evaluation here. I can pop the negative out here. So this will give me lim r to infinity. When I evaluate this piece between bounds, I'll get -r e to the -r minus, lots of negatives here, -1 e to the -1. Then I pop this negative out and I have plus integral -1 to r e to the -x dx chilling, and then I can close this. This mess here can be cleaned up a little bit. We also still need to take our integral here. So this is lim r to infinity. This piece doesn't change, -r e to the -r. What about my negatives here? I've got minus, minus, minus. So these two would make this a positive one, and this would make it negative again. And then here I have e to the -1. So this is just going to become minus e. And then my integral, when I take the antiderivative of e to the -x, I get -e to the -x. And he gets evaluated from -1 to r. Finally, evaluating this piece between bounds, I get lim r to infinity, -r e to the -r minus e. When I plug in r here, I'll get -e to the -r. And then I'll subtract off what I get when I plug in -1. Now that minus from the evaluation and the minus from this will make a plus. And I'll have plus e to the -1, which is e to the 1. That's just e. Oh, this is funny. I wasn't expecting this. Let me make sure that's correct. Good. Minus -1. Yeah, yep, this is correct. Okay, cool. So these two pieces, this is unintentional, but these two pieces add up to 0. They cancel. And the limit we have to take is the following. So we get lim r to infinity, -r e to the -r minus e to the -r. And I'll take these separately. So this is lim r to infinity, -r e to the -r minus lim r to infinity, e to the -r, like this, just using my limit rules, right? One of these is easy, one of them is harder. Which one's easy and why?
The e to -r. because you don't have to deal with as many infinities intersecting.
Yeah, good. In fact, I would rewrite both of these as ratios right away. This is lim r to infinity. This first piece is negative r over e to the r. And then over here I have limit r to infinity 1 over e to the r. As r goes to infinity, e to the r goes to infinity. So this piece right here is 1 over e to the infinity, which is 1 over infinity, which is 0. So I'm not worried about this piece. This piece is going to 0. What about this piece? So what I have left here, I'll pop out the negative, and I've got lim r to infinity r over e to the r.
I would assume that it would be 0, since your denominator, even though we're dealing with infinities, is technically bigger just because of the presence of the e. At least that's my hypothesis.
It's a good hypothesis, but I would caution against assumptions. So your hypothesis is correct, but how do we verify it?
Can you take the derivative of the top and bottom? I forgot what row it is, but
Good, Josh. Yeah. So if you plug in infinity here, this looks like, right? So I'm not worried about this piece. This piece is 0. So this guy looks like, and I'm going to put this in quotations to say I'm not responsible for this. Looks like infinity over e to the infinity. And e to the infinity is infinity, so that's infinity over infinity. Now, is that 1? The top and bottom are the same.
I would say 1. I want to say 1, but I remember you saying it's not 1.
Okay, good. Yeah,
It's like undefined.
very good. This is an indeterminate form. You know how it's possible in the English language to put words together that are subjects, objects, and verbs, but don't make a sentence, right? That don't mean anything. It's possible in algebra to put symbols together that don't necessarily mean anything. 0 over 0, infinity over infinity, 1 to the infinity, 0 to the infinity. These are all those sort of things. This is an indeterminate form, specifically an indeterminate ratio. Which is good news because that means we can apply L'Hopital's rule. Now, my wife took Calc 1 not too long ago at Santa Fe, so I know that not every Calc 1 class covers this shit as well as it should. There is a section here back in 4.4 called Indeterminate Forms and L'Hopital's rule that you guys are all supposed to be experts at because you all took Calc 1. I know the truth is not necessarily that. So we need a little bit of a compromise here. On the one hand, I must teach you the Calc 2, and we don't have time to go back and redo this whole section. On the other hand, I can introduce the challenging problems slowly, and you guys can self-study 4.4 on L'Hopital's rule and indeterminate forms. The basic idea is this. If you've got a fraction like f over g, and both the top and bottom are going to infinity, or the top and bottom are going to 0, then you can try to take that limit again by taking the derivative of the top and the bottom. That's kind of miraculous that that shit works, but it does. The proof is in here. It's not too hard. And you can actually think about it as a consequence of power series later. But their proof is fine. If you want to read the proof, go for it. The big thing is just this, that if you get 0 over 0 or infinity over infinity, both of which are indeterminate ratios, then you can take the derivative of the top and bottom and try again. Here's the notation I'd like you to use. Here's an equal sign. I'm going to say this limit is equal to something else down here. But to let my reader know that the tool I'm using is L'Hopital's rule, I put a little L'(H) here for L'Hopital. The negative stays there, lim stays there, r to infinity stays there. But I take the top, his derivative is 1. I take the derivative of the bottom, his derivative is e to the r. And now I try again. So this time I get 1 over e to the infinity. I'm sorry, I should say these are all negative, right? I should say I get negative 1 over e to the infinity. That's this negative here, which is negative 1 over infinity, which is negative 0, which is 0. So here, this integral converges to 0. Oh, I'm curious about what that is. Sorry, Matthew sent me something here. I'll have to research that later. I won't do it now. No, you're good. Yeah, this is very good. All right. So this is one example of a type 1 improper integral where the challenge is the limit at the end. Our limit at infinity skills need to get really good, not just for this section. After this, we're going to section 11.1, which is all on sequences. That whole section is limits at infinity. And after that, we're doing series. And we're doing that for like 7 or 8 sections, all of which is limits at infinity stuff. So these skills need to get good. I'll remind you really quickly what L'Hopital's rule says in its generality, the different kinds of indeterminate forms. This is going to be my hard and dirty review for section 4.4. Funny story about L'Hopital. L'Hopital was a dude. He was a guy, a French guy, and he was a mathematician, but he wasn't like the best, but he had lots of money. And so what he did is one of the Bernoullis, who are another mathematical family, there's a pair of them, brothers, Jacob and Johann, had developed this theorem, and L'Hopital paid them for it. And then he published it under his own name. So we call it L'Hopital's rule, but really it comes from, I think, Johann Bernoulli. Anyway, an indeterminate form is an expression that has no determined value. These can be 0 over 0, infinity over infinity. These are called indeterminate ratios. And these are the only things to which we can apply L'Hopital's rule. Any of the other indeterminate forms, you have to do algebra work to turn them into these before you can apply L'Hopital's rule. Other examples are 0 times infinity. This is called an indeterminate product. Infinity minus infinity, which is called an indeterminate difference. What else? 1 to the infinity. There might be a couple others like this. I think 0 to the 0. So these are all indeterminate ratios, indeterminate product, indeterminate difference. I want to say 0 to the infinity is also an indeterminate form. Let me just double check. Basically, you need two things to be fighting each other. So somewhere in here, I think we have a complete list of indeterminate forms. Powers, yeah, okay. 0 to the 0, infinity to the 0, 1 to the infinity. What did I miss? Infinity to the 0, yeah. So these three are called indeterminate powers. Okay. So this is a list of indeterminate forms. If you see any one of these things, it means you got to stop. You got to put on the brakes. You cannot cancel 0 over 0 or infinity over infinity and call it 1. You cannot say 0 times infinity is 0. You cannot say infinity minus infinity is 0. And you can't assign a particular value to any of these right away either. The real thing that's going on here is like this shit is fighting each other, right? Like 0 times infinity, the 0 wants to make it small, the infinity wants to make it big. Or 1 to the infinity, 1 to anything should be 1. But anything, if you take something and raise it to an infinite power, that should want to get big or maybe get small. 0 to the 0, 0 to any number is supposed to be 0. But any number raised to the 0th power is supposed to be 1. So is this 0 or 1 or maybe something in between? And then similar stuff here, right? If you take a really, really big but finite number and raise it to the power 0, that should give you 1. But what if that number is infinite in size? Is that strong enough to overcome this power? So all of these come from things that are fighting each other. And the fight is so severe that we can't detect the result just from these symbols. L'Hopital's rule says if lim x to infinity f of x over g of x looks like infinity over infinity or 0 over 0. I like to put these in quote bunnies saying like I am not responsible for these. If it looks like these, then we can try again. As lim x to infinity f primed of x over g primed of x. And this will be equal to the original limit. So if your limit looks like infinity over infinity or 0 over 0, take the derivative of the top, take the derivative of the bottom separately. Don't use the quotient rule and differentiate the whole thing. Take the derivative of the top and bottom separately, then try again. This works at places other than infinity. If you're taking the limit as x goes to 5 and you get 0 over 0, infinity over infinity, you can do this there too. But the way we're going to use it is always like this. So this is how I'm going to write it. And then the obvious question is, well, what do I do with an indeterminate product or an indeterminate difference or an indeterminate power? The answer is you have to bash them with the algebra hammer until they turn into indeterminate ratios. So indeterminate products, you can like divide and rewrite as a reciprocal. Indeterminate differences, you can multiply by a conjugate. Indeterminate powers, you have to take natural logs and then turn those into products and then turn those into ratios. So these can be quite challenging. But L'Hopital's rule looks like this for us. It only applies to infinity over infinity or 0 over 0. Please don't use it anywhere else. Some other important theorems on limits at infinity that you will need, I'm going to remind you of quickly. Theorem. Limit x to infinity, 1 over x to the p. This is equal to 0 for any positive number p. So if you have the reciprocal of a positive power, in other words, if that x really does belong downstairs, then this is going to go to 0. 1 over infinity is 0. Other important theorems. Lim.
Shouldn't that be for any positive number p over 1?
It has to be 1 over x to the p, and p has to be a positive number.
But what if p is 1? Wouldn't that be a harmonic series?
We're not talking about series here. I'm just talking about limits.
Oh, okay,
No
sorry.
series. 1 over x, as x goes to infinity, the limit as x goes to infinity of 1 over x certainly is 0. That's 1 over infinity. That's 0. The sum sigma 1 over x 1 over n also does diverge, but that's a very different animal. We'll talk about that, and there's a lot of room to get confused there down the road. That's why I'm going to try to introduce these very gently, one thing at a time. So this is an important rule, and we're just talking about limits. I'm not talking about any integrals or sequences or series. No question of divergence or convergence here. This is just a statement about limits. This is from Calc 1. This theorem's actually there. If you go back to section 2.6. Oh shit, where is it? There it is, right here. If r is a positive rational number, then lim x to infinity, 1 over x to the r goes to 0. And if r is a positive number, any real number such that this is defined, then that limit will be 0 at negative infinity also. The next one I wanted to show you is, how do I say this? Limit a to the x as x goes to infinity. This will be 0 for any number a satisfying 0 is less than a is less than 1. This is coming from what we know about horizontal asymptotes of exponential functions, right? So if you have an exponential function where the base is between 0 and 1, that's a decaying exponential. And decaying exponentials tend towards 0 as you wander further and further off to the right. For an example here, let me show you really quick. If I take something like 0.12345 and I raise it to the power of x, fiddle with my scales a little bit. Right, this is a decaying exponential, and as we wander off to the right, he goes towards 0. So as long as the base is smaller than 1, any such function will go to 0. This is just from decaying exponentials. A special case of this, I'll list it as a separate theorem even. Lim x to infinity e to the negative x. This is 0. This is because lim x to infinity e to the negative x is lim x to infinity 1 over e to the x, which is, I'm out of space, lim x to infinity 1 over e to the x, like this, because the top is just 1. And now 1 over e is between 0 and 1. So by the previous theorem, this guy is 0. But he shows up enough that he's worth remembering on his own. Some warnings. Lim x to infinity sine x does not exist. Lim x to infinity cos x does not exist. These are things people tend to forget. And then one other important guy, lim x to infinity, the inverse tangent of x. This one does exist, it's pi over 2. So I would advise that everybody go back and reread the following sections. Section 2.6, in the textbook. This is a very important section. It shows you all of the basic tricks that you need to calculate limits at infinity. It has lots of good examples. It has, you know, these sort of things that I'm reminding you of right now. And then the other one I would look at is 4.4, indeterminate forms and L'Hopital's rule. So I would go back and reread 2.6 and 4.4 in preparation for what we're about to do. Not just 7.8 that we're talking about now, but also all of chapter 11, which is what we're going to move to after this. So you want to make sure you're good with that. These are just some of sort of the most important things, the things that show up most often in the following sections. So this is all Calc 1 stuff that I'm just trying to remind you guys of. So please never tell me that this limit is infinity or 1 or anything like that. He doesn't exist. He doesn't exist. This one's pi over 2. He shows up a lot. E to the x goes to 0. So does any other decaying exponential or power function where the power really is negative. In other words, 1 over a positive power of x. All of those go to 0. Okay. What else would we like to do? We've taken a look at a handful of type 1 integrals. Let me start playing with something here. We looked at 1 over x cubed, right? We said the integral of 1 over x cubed from 1 to infinity converges. 1 over x from 1 to infinity diverges. There's a theorem here. Maybe to kind of warm us up for this, I'm going to come back to Desmos for a minute.
Sorry, Professor.
Yeah.
I wasn't sure if you were aware, but we've gone over time.
Oh, are we? Shit. All right, I guess we'll stop here. I'll pick up on Thursday with p integrals. Let me give you a little something to think about as we're leaving here. Here's 1 over x, right? And we said that the area 0 less than y less than 1 over x. We said that the area here x greater than. We said that this area is infinite. The area under 1 over x cubed, 0 less than y less than 1 over x cubed, x greater than 1. We said that this area is finite. Somewhere there's a tipping point of integrals like this, 1 over x to some power, where if you're bigger than that tipping point, you will be divergent, you'll have infinite area. And if you're smaller than that tipping point, you will be convergent, you'll have finite area. Like I can say for sure that anything that lives under 1 over x cubed has to be finite because the area under 1 over x cubed itself is finite. And I can say anything bigger than 1 over x, the area under that has to be infinite because the area under 1 over x is infinite. But somewhere in here is a special tipping point. So let me show you. There's a theorem coming up and then I'll let you guys go. Integrals of the form integral 1 to infinity 1 over x to the p dx converge if something is true and diverge if something else is true. These are called p integrals. God, thank you, baby. And we will investigate them carefully at the start of class on Thursday. The other thing we're going to do on Thursday is learn how to work with type 2 integrals, which are integrals where the height is infinite. But yeah, I'll go ahead and stop here. I hope you guys have a lovely rest of your afternoon, and we'll pick it up there next time. I'll also be doing my best to get your exams graded by the start of class on Thursday. If necessary, I may end up using some of Thursday afternoon or evening to grade, but hopefully by the start of class, you'll be good. All right, hope you guys
Have a great day, Professor.
take care.
Thank you.